People look at my story and see a warning, a cautionary tale about a woman who handled dangerous materials without understanding the consequences. They imagine I was naive, reckless maybe, a brilliant mind that simply didn't know better. That's the comfortable version. It lets people feel safe, like the tragedy was about ignorance, and ignorance is a problem that can be solved. But here's what they get wrong. I knew. Not everything, nobody knew everything, but I watched what the materials were doing to my hands. I saw the burns. I felt the fatigue that never quite left. I kept working anyway, and that choice, that deliberate, informed, eyes-open choice, deserves something more than pity. It deserves to be understood. So let me tell you what was actually happening. Not the version that gets cleaned up for textbooks. The real thing. What radioactivity is. What it does inside a body. Why I couldn't stop. And why the question I gave my life to is still not completely answered. I named it. I isolated it. And I could not fully explain it. That's where we're starting. Most people carry a picture of atoms in their heads. Small, solid, permanent, like tiny billiard balls that have been around since the beginning of the universe and will keep being around forever. That picture is deeply comforting. It means the world is made of reliable building blocks, stable ground underneath everything. Radioactive atoms shatter that picture, not metaphorically, literally. The uranium in my laboratory was not stable. It wasn't sitting quietly in its container waiting for something to happen. It was actively, constantly, inevitably falling apart. Every second, no intervention required, no trigger. It was simply the nature of that particular nucleus. Too large, too crowded, too energetically unstable to hold itself together indefinitely. Here's the analogy I want you to hold. Imagine a building, solid looking from the outside, stone walls, heavy doors, but someone quietly removed one too many load-bearing walls from the inside. It's not going to collapse the moment you look at it. It might stand for years, but the collapse isn't a question of if. It's only when. The structure cannot hold. That's uranium. That's polonium. That's radium. They look like matter. They behave like a slow, inevitable surrender. And here's the part that changed everything for physics. This wasn't chemistry. Chemistry is atoms interacting with each other, bonds forming, breaking, electrons shifting between atoms. We understood that. What I was observing was something happening inside a single atom, inside the nucleus itself, that had never been seen before. That distinction between atoms reacting with each other and an atom coming apart on its own, that shook the foundations of what matter was supposed to be. So when an unstable nucleus finally lets go, what actually happens? It doesn't just vanish, it ejects something. And I want to describe these not as categories with names, because names make things feel solved, but as behaviors, because that's how I first encountered them. As behaviors I had to figure out. The first type barely travels any distance at all. A sheet of paper stops it. Your skin stops it. But if it gets inside you, if it's inhaled, if it's swallowed, it deposits an enormous amount of energy in a very small space. It hits like a freight train into a single room. That's the alpha particle. 2 protons, 2 neutrons, fired out of a decaying nucleus, dense, slow, devastatingly damaging at close range. The second type is faster, lighter. It punches through paper without trouble. It takes a few millimeters of metal to stop it. It's an electron fired out of the nucleus at high speed, when a neutron converts itself into a proton. Beta radiation, quicker, more penetrating, but still something physical matter can interrupt. The third type has no mass at all. It's pure electromagnetic energy. It passes through your skin, like your skin isn't there. It passes through several centimeters of lead before it's meaningfully reduced. Gamma radiation. And it doesn't just pass through as it moves. It's breaking chemical bonds in whatever tissue it encounters, snapping the molecular architecture of living cells as it goes. That third one, that's what was moving through me, through my fingers while I held the samples, through my lungs while I worked in that shed in Paris, through my bone marrow for 36 years of research. Not a substance that clings to the skin and can be scrubbed away. Energy, invisible, tasteless, odorless energy that was quietly dismantling me at the cellular level the entire time. I didn't feel it. I want you to sit with that. I didn't feel it happening. There was no pain in the moment, no signal, no alarm. The damage was cumulative and silent. That is perhaps the most dangerous thing about it. Not that it was powerful, but that it was imperceptible. You cannot defend yourself from something you cannot detect. Let me give you something concrete, something that makes this more than a historical story. My personal research notebooks, the ones I wrote in during the 1890s, the ones where I recorded the observations that led to 2 Nobel Prizes, are still radioactive today. Right now, they are kept in lead-lined boxes in the Bibliothèque Nationale de France in Paris. If you want to see them, you can request access, but you will be asked to sign a liability waiver first, because the contamination is real and it is ongoing. This is not metaphor. The polonium and radium that settled into those pages more than a century ago are still decaying, still emitting. The pages themselves are still warm with radiation. Why? Because of something I want you to understand, not as a formula, but as a characteristic, a personality trait of each element, if you'll allow me the indulgence. Polonium-210, the element I discovered, the one I named after my homeland, has a half-life of about 138 days, which means every 138 days, half of whatever polonium is present loses its radioactivity. In a few years, most of it's gone. Polonium is impatient. It decays fast and burns bright. Radium-226 is different. Its half-life is 1,600 years. Radium is patient in a way that outlasts civilizations. The radium I isolated in 1902 is still mostly intact. It will still be mostly intact when everything any of us have built has crumbled. Each element has its own clock, and no external force sets it, not temperature, not pressure, not proximity to other elements. The clock is internal. It runs on its own logic, and this means, and here's the part that should unsettle you, the polonium that contaminated my body in 1898 was still decaying inside my tissues in 1934, the year I died, slowly, persistently, on its own schedule. I coined the word radioactivity. I need to be precise about what that means, because people assume naming something is the same as understanding it. It isn't. Naming a phenomenon is an act of observation. It says this thing exists, it behaves consistently, it can be measured. That's meaningful. But it is not the same as knowing why it happens. I could describe radioactivity with extraordinary precision. I could measure it, isolate it, identify which elements exhibited it, and quantify the energy released. I built instruments sensitive enough to detect the faintest trace of it. I was rigorous, I was exact. But the deeper question, why does one nucleus decay at this moment, and an identical nucleus sitting right beside it wait another 10,000 years? That question I could not answer. There is no external cause. There is no detectable difference between the atom that decays now and the one that decays later. No trigger, no reason. Quantum mechanics would eventually describe this as intrinsically probabilistic, which is an elegant phrase, but let me translate it for you. We cannot know in advance, not because we lack information, not because our instruments aren't sensitive enough, but because at the quantum level, nature itself does not predetermine the outcome. The decay happens within a window of probability, not certainty. That disturbed me deeply. I believed, I still believe, if we're being honest, that effects have causes, that the universe runs on logic that can be traced. The idea that an atom can decay for no discernible reason, with no prior signal, just because the probability arrived, that felt like an open wound in the structure of physics. I leave this unresolved, not because I gave up on it, but because it remains unresolved. Quantum indeterminacy is not a gap in knowledge that later science filled with certainty. It is a permanent feature of how the universe operates at small scales. We learn to calculate probabilities with extraordinary accuracy. The underlying why is still, in the deepest sense, open. So why did I keep working? If I knew, even incompletely, that the materials were dangerous, why didn't I stop? Not recklessness. Please don't simplify it that way, and not ignorance. Something harder to articulate. The work was real in a way that very few things are real. The elements weren't theoretical. The energy wasn't a proposal. The questions we were asking. What is matter? What is the atom? What is happening at the core of things? Those were the most fundamental questions anyone had ever asked, and we were getting answers. Actual, verifiable answers. For the first time in history, the inside of the atom was not just a philosophical idea. It was something we could touch, measure, and describe. When you are that close to something that's significant, you don't just walk away because it's inconvenient, because it's uncomfortable, because it's risky. Risk is part of the work. It always has been. And here is the part I want you to hold alongside everything else. The same radiation that destroyed my bone marrow, that dismantled my body cell by cell over 36 years, is today used to destroy cancer tumors. Precisely, deliberately. The same energetic particles I studied are what make nuclear medicine possible, what allow doctors to image the interior of the body without cutting it open, what power the carbon dating that lets us understand human history, what sits in the smoke detector on your ceiling right now, detecting combustion particles. I am not asking for sympathy. I have no interest in being a martyr. I am asking you to hold the full picture. The thing that killed me is also understood carefully and used responsibly, a tool that extends human life. That's not irony. That's what science actually is. Knowledge doesn't arrive pre-packaged with a safety guarantee attached. It arrives raw. What you do with it, how carefully you learn it, how responsibly you apply it, that's on us, always on us. Here's where I want to leave you. Somewhere in Paris, in a lead-lined box, in a library, my notebooks are still emitting radiation. Right now, as you watch this, the pages I pressed my contaminated hands against more than 100 years ago are still warm with the energy of decaying atoms, still becoming something slightly different, second by second. And somewhere in the atmosphere, in the rock, in the soil, in the bones of the earth, atoms of polonium that I first identified, that I separated from tons of pitchblende with my own hands, are continuing a process that began billions of years before I was born, that will continue long after every person watching this is gone, long after the buildings we live in have fallen, long after the languages we speak have changed into something unrecognizable. Radioactive decay is not dramatic. It doesn't announce itself. It doesn't ask permission or wait for a significant moment. It is simply matter, insisting quietly, irresistibly, on becoming something else, one nucleus at a time, on its own clock, for its own reasons, which we cannot fully name. I spent my life trying to understand what matter is made of. What I found is that matter is not as permanent as we need it to be. Atoms change, elements transform. The most solid seeming, dense, heavy, ancient substances in existence are at their cores in the middle of a transition that never stops. Everything we call stable is stable only within a range of time we happen to be able to perceive. That idea never stopped being strange to me. Not after the first Nobel, not after the second, not in the shed in Paris, not in the laboratory in Warsaw, not in the hospital at the end. I did not solve the mystery of radioactivity. I made it precise enough to see how deep it goes. And what you find when you look that carefully at matter is that nothing is simply sitting still. Everything is mid-process. Everything is on its way to becoming something else. That might sound unsettling, but for me it was the most beautiful thing I ever learned. That even at the smallest scale, the universe refuses to be static. It's always moving, always changing, always in some quiet and invisible way, reaching toward the next thing. And that, more than any prize or discovery or element on the periodic table, is what I want you to take with you.